I could not. Yeah, actually, I was thinking about it. I was on the internet. Finally, I was. I should have got it right.
Yesterday, I right-handed, I was playing bonds. I was like, you know what? I'll go right-handed. Just to say that. My left hand just sucked so bad. What? No, it's, with patience. And I was like, today's Wednesday? That's insane. Well, Thursday we have to have you when we don't have schools.
All right. Can you guys take out the assignment from last time? Let's run through and check our answers here real quick. So I have the solutions written up here. Take a few minutes and check these. We'll take some questions here if there are.
And the same, I got
Yeah, go ahead.
Wait, I can't tell. Does your 11 say 1/6?
1/2.
Ooh, what's number 1?
All right. Questions from this? Anybody? So for part A, what is the value of t that we need? So 89 to 1999 would have been 10. So I'm just plugging 10 in for t and into my calculator. So 738 times second ln 0.345 times 10 gives me 23,247. To do part B, we're going to graph this. So 738 times e to the 0.345 times x, and then 1500. I know that from my answer to part A, certainly it has to be less than 10 years. And I got to see at least 1500, so I'll do 2000 there, so that seems fine. So there's my termites curve, there's my 1500 curve. Second trace, intersect, enter, enter, enter. So I get 2.06.
Okay, thank you.
Well, you're welcome. Yeah. 11? Yeah, it is 1/2.
Yeah,
Okay. So converting that into exponential form, I'd write 36 to the x is equal to 6, right? So the relationship I see between 36 and 6 is that 6 is the square root of 36. And remember that the square root is the same thing as the fractional exponent 1/2. So that's why it's 1/2. Is that okay? So again, there's ways to type this stuff into your calculator. Right now, we're just trying to do this by inspection. So all of these were like reasonable things that you could look at and figure out without having to really do any calculation. Today, we'll talk about how to use the calculator a little bit to evaluate some of these other logarithms that aren't necessarily like a whole number or a fraction.
Bless you.
Thank you. Okay. Should we continue on then today? Talking about logarithms? Sure. So, just to restate our definition, our definition for a logarithm says let b and y be positive numbers where b is not equal to 1. Then we have log base b of y equals x if and only if b to the x is equal to y. So there's two very special values of b that we're interested in. So log base 10 is called the common log. And is abbreviated just log with no base written there. So if you see no subscript on your logarithm, the subscript there is 10. We just don't write it. Okay? So most of you probably at this point have noticed that there's a log button on your calculator that just says log. That is log base 10. That is the common logarithm. Everybody's okay there? Okay. Log base E is called the natural logarithm. And is abbreviated ln. So if you see ln, that means log base E. And probably some of you have noticed that there's an ln button on your calculator right next to the log button. Everybody's okay with that? Okay. So let's do some calculator stuff. So let's say we want to do log base 3 of 7. So if you have your calculator with you, I'd ask you to please take this out now so that you get a good feel for how to use your calculator to evaluate these things, because depending on how old your calculator is, there may be 1 or 2 different ways we have to do this. So you should take your calculator out now and follow along to see if you can do it, which way you have to do this kind of a problem. Okay? All right. So let's start by trying to press the math button. And we're going to scroll down and look for the option that says log base. So I pressed the math button on my calculator, and I've scrolled down to look for the option that says log base. If I press enter, if you have a new-ish calculator, it'll allow you to just type in the base and the argument, and you can just press enter, and it's very easy. Does anyone not have that option when you press the math button? Eli, I'm looking at you that has the old 83 there. You don't have that, right? Okay. Is anyone else in the boat that they don't have the log base option on their calculator? Okay. So Eli and anyone else that's too shy to say so, the other way that you can do this is you can just do log of the argument divided by log of the base. And you'll get the exact same result. So, Eli, that's how you'll have to do that kind of thing on your calculator. And if you just don't feel like going through the menus to find the log base command, you can certainly do that, everyone else. It's not wrong. It's doing the exact same thing. Okay. Is everybody okay with that idea? Okay. So if I wanted to do, say, ln of 6, I can just press the ln button on my calculator, type in the 6, and press enter. And the calculator will do all the heavy lifting of evaluating these things for us. Is everybody okay there? So there's kind of 3 different options as far as the logs go on your calculator. You can use the log base command to enter it in specifically. And then on your home screen, just the buttons, you have the ln button and the log button for the natural log and common log, respectively. So, yes, Eli. Sure. So, remember yesterday we talked about inverses as part of our review before we started talking about logarithms. And we said our one definition for an inverse is that we can say f and g are inverses if and only if f compose g is equal to g compose f, which all give us x. So what I want to do is let's consider f of x to be the function b to the x, and g of x to be the function log base b of x. So let's check to see if these two are inverses. So remember, f compose g is the same thing as f of g of x. That what I'm going to do is I'm going to take my expression for g of x and plug it into my function for f of x. Everybody okay there? So let's just look numerically at this for a moment. So let's just say we're going to use the value of b to be 2 and the value of x to be 5, just to kind of see what's going on numerically and use our calculator to handle this. So I can do 2 to the, and then I'll choose that log base command, 2, 5. And look at the result that I got, just 5, right? So what's really happening here is this exponent base of 2 is canceling this logarithm base 2, leaving me with just the 5. So the same thing can apply here, is that the log, or the exponent base b, is going to cancel the log base b, leaving me with just x. What if we go in the opposite direction? So here we're going to be taking our exponential and plugging it into our logarithm. And let's do a similar check on our calculator to see how these behave. So again, I'm going to use b to be 2 and x to be 5. So I'm going to do log base 2 of 2 to the 5th. And what do I get again? The 5. So what is happening here is that the logarithm base b is canceling the exponent base b, leaving me with just the x. So for example, if I ask you to simplify the expression, ten to the log 4, remind me again, when we don't write a base on a logarithm like that, what is the base there? 10. So this looks exactly like this situation here, right? So what's going to happen? exponent base 10 cancels with logarithm base 10, and we're left with just the 4. Let's just kind of check that on our calculator real quick. Just to show that the same thing is happening. We're getting just 4. Is everybody okay there? Okay. Let's try something that's a little bit sneakier. What if we have log base 5 of 25 to the x? Can I cancel things right away as it's currently written? No. Why not? Well, the base of my logarithm doesn't match the base of my exponential. They're not the same number. Is there a way to rewrite one of them so that I can make them the same number? Okay, so I think what Nancy's saying is 25 is the same thing as 5 squared. So I can rewrite the 25 as 5 squared, but that still has an exponent of x outside of it, right? Zach?
Could you say the log 5 in the parentheses of 25 to the 1/2?
No, because 25 to the 1/2 is not the same thing. Like, you're saying 25 to the x is equal to 25 to the 1/2 to the x, and that's not true. What? Right, but those two things are not equal, right? 25 and 5 are not the same number, so you can't do that. But 25 and 5 squared are the same number, and we can do that. Does that make sense? So remind me again now, when I have an exponent of an exponent like that, how do I simplify those? Yeah, so the rule that we're using is this rule of exponents. Remember that from last chapter? So we'll multiply those. So that's going to give me 5 to the 2x. And now we notice that the base of the exponential matches the base of the logarithm. So they can cancel, leaving us just with 2x. Does everybody see that? Do we feel okay there? Let's do one more example, kind of using this inverse relationship. So this first example, I'm going to ask you guys to write the inverse of the function. And our first function is y equals 6 to the x. So remember from yesterday, we reviewed how we found the inverse of a function. So it was 2 steps. The first step is we have to get the x by itself. And then we swap the x and y variables, right? So to get that x by itself, I have to cancel out that exponent base of 6. What can I do to cancel that exponent base of 6? Dividing by 6 will not do it. Because it's not 6 times x, it's 6 to the x. So dividing 6 to both sides just turns that into 6 to the x minus 1. What can I do to both sides of this equation to cancel out that 6? Look at this. This is your hint. No? Clayton? Sure. So this is like my 6 to the x, right? And I did something to it to cancel it out. What did I do to the 6 to the x to cancel it out? It's the logarithm. Okay, so I think if you wrote it down, you would be fine, but the way we've said it is not what you mean. So you're saying the 6 is in the parentheses or in the subscript of the logarithm? Good. So we'd say log base 6 and we'll do that to both sides. Everybody's okay there? And now we know log base 6 will cancel the exponent base 6. And our x is all by itself, right? So my last step then would be to swap my x and y. And there's my inverse. Is everybody okay on that? Let's do another. Let's say we have the function y equals the natural log of x plus 3. So again, if we want to find the inverse of this, the first thing we want to do is try to get the x by itself. So what's the first thing we need to cancel to start getting that x by itself? There's no coefficient. So by coefficient, I think you mean the natural log. Okay, so the natural log is an operation, it's not a number. So coefficients are numbers. But yes, we need to get rid of the natural log. Okay? So what operation is going to cancel out a logarithm? So Zach has a good point in that the natural log is the same thing as log base e. Yes, that's true. Okay, so what operation is going to cancel out that log base e? Let's look at a hint here. So if I look at this problem, I have a logarithm that got canceled to leave me with just an x, right? What canceled the logarithm? An exponent base that matched the log's base. So if we return to our previous problem, what exponent base do we need to use? E, because it needs to match the base in the logarithm. So I'm going to do exponent base E to both sides. Now notice I really exaggerated the size of the E there because I want to make very, very clear we're not multiplying both sides by E. The E is the base of an exponential. The Y is in the exponent on the left-hand side, and the log base E of x plus 3 is the exponent on the right-hand side. Now we showed earlier that an exponent base B will cancel with log base B. So we're going to have e to the y is equal to x plus 3. Now what should I do to get the x by itself? Subtract 3 from both sides. And obviously I can't subtract 3 from e to the y. Those aren't like terms, so I'll just write it next to it. And then my last step would be to swap the x and y variables. And that would be my inverse. Is everybody okay on that? Okay. And the last topic I want to look at today is graphing logarithmic functions. Bless you.
Thank you.
So the general form for a logarithmic function is a times log base b of x minus h plus k. Guess what these a, b, h, and k do? They perform the same transformations that we've talked about a bunch of times. I'm not going to write them down again, but we've mentioned this, I don't know, 3 or 4 times now this year. They perform the same kind of transformations. So my plan here is I want to choose x values so that I get rational numbers for my y coordinates. I don't want to just pick any willy-nilly x's. I'm going to pick them very specifically so that the y coordinates I get are reasonable. So the way I'm going to do that is I'm going to pick my x's in this fashion. why would I want to pick my x's this way? What's going to happen when I do that? Let's just show you for example. So let's say I plugged in that first value for x into my function to find my y coordinate. I have a positive h and a negative h. Those cancel out. Then I have a log base b and an exponent base b. Those are going to cancel out, leaving me with negative 2 times a plus k. So the reason we're choosing our x's this way is they are going to cancel out the logarithm and give us a number that's not irrational. Okay. So the rest of my y coordinates kind of follow. Notice here that the exponent on b gives me the coefficient on a. That's kind of the pattern that's going on there. Okay. So let's talk about domain and range, and then we'll do a graph and example. Remember that exponential and logarithmic functions are inverses. So the domain for my exponential is going to turn into the range for my logarithmic, and the range for my exponential is going to turn in the domain for my logarithmic. So if you remember, the domain for exponential functions was easy because it was always all real numbers, right? Since logarithmic and exponential functions are inverses, and with inverses we switch the x's and y's, the domain for my exponential becomes the range for my logarithmic. Everybody okay with that idea? Now, for exponential functions, we had a horizontal asymptote, and our range was either everything above the horizontal asymptote or everything below the horizontal asymptote. So for logarithmics, we're going to have a vertical asymptote, and in this case, it's going to be given by x equals h. So my domain is if a is greater than 0, we're going to go, oh, never mind. You know what? We're just going to do it this way because we don't deal with that. So the domain is always going to be h to positive infinity for the form that we're dealing with. So let's do an example. So let's graph log base 4 of x plus 1 minus 2. First thing I would do is write down my values for a, b, h, and k. What's my value for A? Yeah, so A is 1, because there's no coefficient on my logarithm. What's my B? 4. What's my H? -1, and my K is -2. Now that I have that, I can write my XY table. So I'm going to have 4 to the -2 plus H, 4 to the -1 plus H, 4 to the 0 plus H, 4 to the first plus H, and then 4 to the second plus H. Okay. So let's just use our calculator to simplify these, because I want these as a decimal so that I can graph them. 4 to the -2, said -2, and then plus a negative is the same thing as subtraction. So I have -0.9375. And then I have -0.75. And then I have 0. And then I have 3, and then I have 15. Those ones are easy to do in my head. Okay. And then I'll fill in my y coordinates. So I have -2 times A plus K. Since K is a -2, instead of writing plus a -2, I just wrote subtraction. Then -1 times A plus K, 0 times A plus K, 1 times A plus K, and 2 times A plus K. I guess I could write those in blue also to match. So I have my XY table. Where is my vertical asymptote at? Remember, that's x equals h. So in this case, that's at -1. And now let's draw our graph. So the first thing I like to do, after I've made my axes, is to draw in my vertical asymptote. So there's my vertical asymptote at x equals -1. So it's a vertical line that passes through the x value -1. And now I'm going to start plotting my points. So -9.375 and -4. -0.75 and -3. 0 and -2. 3 and -1. And then 15 and 0. So I'm going to draw my graph now. Remember, I can't cross my asymptote, So I'm going to start by drawing my curve so that it kind of follows my asymptote. And then goes through the other values. And just like the exponential had arrows at both ends of my graph, my logarithmic is going to have arrows at both ends of my graph. Everybody okay with the picture that we've drawn here? And then the last thing we need to do is do our domain and range. So the domain is h to positive infinity. So that's -1 to positive infinity. And the range is just always all real numbers. Okay. And let's stop here. That's probably good for today. We did a lot.